Hey guys, welcome back to Thermochemistry. In this video, we're going to talk a little bit more about energy, and we're going to apply some of the terminology and topics to specifically how we study it in chemistry. So, the way that energy behaves, there are things called laws that govern or explain how energy behaves. So, the first law of thermodynamics is that energy can neither be created nor destroyed. It can only change form. Another way of saying this is the total energy in the universe is constant. So, how does this apply to us as chemists? Well, I would say that during a chemical reaction, energy is neither created nor destroyed. It simply changes form. It gets released, it gets absorbed, so it changes the format that it's in. When we're thinking about the total energy of the universe, we can think of the universe as kind of two different things. So the part of the universe that we are interested in is the system. So for us as chemists, system often is the beaker that chemistry is happening in. And then there's the surroundings, that's everything else that's not part of the system. Monitoring the change in the universe is really hard. To have to consider both the system, what's happening in the beaker, and then everything else that's not a part of the system. The table the beaker is sitting on, the room that the beaker is in, the building that it's in, the environment that it's in, the country, the town, whatever. You have to consider all of those things, and that's just not practical. So what we're going to do is we are going to focus our attention on the system. We're going to talk about what's going on inside of that beaker, and we can eventually apply this to a concept of the universe, but for right now, let's focus in on our system. So energy is what we call a state function. So a state function depends only on the state of the system, not how the system arrived there. So that's kind of a aloof concept, if you will. So let's make it a little bit more tangible. An example of a state function would also be altitude. So altitude is not dependent on how you get from one altitude to another. It depends only on where you were and where you are now. So let's say I'm making a trip from Wilmington to my hometown of Springfield, Illinois. There's two different routes that I can take. So I can take kind of the southern route through South Carolina, through Tennessee, a little bit of Kentucky, and then up through the bottom of the state. I could take the northern route, which would be more towards Virginia, West Virginia, Ohio, a little bit of Kentucky again, through Indiana and Illinois. Okay. So I could take two different paths to get to Springfield. But the altitude change for either of those paths would be the same. So the altitude in Wilmington is roughly 30 feet. Okay, we're essentially at sea level here, right? It's 30 feet. The altitude in Springfield is at 528 feet. So if I want to know how my altitude changed going from Wilmington to Springfield, I would look at the change in altitude. So this triangle right here is just the symbol that we use to denote change. So when I see this triangle, I read change in altitude. And the change in anything is always final minus initial. Final minus initial, always. So if I'm looking at my change in altitude, I would take my final altitude at my destination, 528 feet, minus my altitude initially, which was at 30 feet. So the change in altitude would be 498. So it doesn't matter which path I took. It doesn't matter if I took the northern route. It doesn't matter if I took the southern route. It doesn't even matter if I went from Wilmington all the way to California and then all the way back to Springfield. My altitude change would be the same, independent of the path I take, only dependent on where I started and where I finished. Energy for a given system is the same. So when we're talking about the energy for a chemical reaction, it's independent of how it was acquired, what steps actually took place, and it depends only on the final and the initial. So if I wanted to write a formula for the change in energy, I would take the energy of my final minus the energy of my initial, and I would subtract those two. Now, in chemistry, when we're talking about chemical reactions, we don't really talk about final and initial. What do we talk about? We talk about reactants and we talk about products. So if I'm doing a change in energy formula, my final would be the energy of the products minus the energy of the initial, which is the energy of my reactants. So for us as chemists, when we talk about energy change, we're going to take products minus reactants. Now, let's take a look at a couple different ways that energy can change. Okay. So we're looking at the change in energy. Oops. We're looking at the energy of the products minus the energy of the reactants. If the difference between the products and reactants is a negative value, we would call that an exothermic process. Energy is exiting the system into the surroundings. It's releasing energy. Energy is exiting exothermic. So let's take a look at something called an energy diagram. So what we see here is as we go bottom to top, the energy is increasing. So something up here is high in energy, something down here is low in energy. Here we see our reactants are very high in energy. Our products are very low in energy. So as we go from reactants to products, the energy goes down. The difference in the energy would then be a negative value. Energy exits the system or it goes down to get to our low energy products. So let's put some hypothetical numbers to this. Sometimes that makes it a little bit more tangible. So our reactants are high energy. Let's call them 150 joules. Okay? So the energy associated with reactants, 150 joules. Low energy products, let's say down here, our products are 20 joules. So if I want to look at the change in energy for this chemical reaction, I'm going to take the energy of my products, which is 20 joules, minus the energy of my reactants, which is 150 joules. So 20 minus 150 will give me negative 130 joules. So that negative value tells me that it's exothermic. Heat is exiting the system. How would we observe an exothermic process? How would we observe heat exiting the system? Well, it can exit in the form of things like light or heat. So here we see a fire, right? So I might put my hand next to that and my hand will feel warm. That is the energy or the heat that is exiting that system and it's being absorbed into my hand. So the form of light, it can exit. The form of heat, it can exit. Let's look at the other side of the coin here. Let's look at an endothermic process. In an endothermic process, heat is entering into the system. So energy in the form of heat flows from the surroundings into the system. So again, we're going to look at the change in energy for this chemical reaction. We're going to look at products minus reactants. And we're going to look at our energy diagram. So again, bottom to top, energy goes up. So in this case, we see that our products are high in energy, our reactants are low in energy. So to get from our reactants to our products, energy is going to have to enter into, or we're going to have to add energy to the system. So in this case, the change in energy would be a positive value. So again, let's make this tangible. Let's put some numbers with it. So our reactants are low in energy. Let's call that 10 joules. Our products are high in energy. Let's call that 95 joules. So if I were to look at the change in energy, that's going to be the energy of my products, which in this case is 95 joules, minus the energy of my reactants, which is 10 joules. So the change in energy would be a positive 85 joules. That positive value tells me it's endothermic. Energy is entering the system. Now, how would we observe this? So this one's a little bit trickier, but let's think about an ice pack, right? So an ice pack, I punch the inner bag, right? It explodes. The ice pack starts to feel cold. What's actually happening there, so I am the ice pack. What's actually happening is the ice pack is absorbing heat from your skin. So the ice pack is an endothermic process. It's pulling heat from your injury into itself. So that is endothermic. What I observe is my skin feels cold. Well, that's because the heat is being removed, right? So the ice pack is endothermic. It's pulling heat into the system. So that's a little bit more about energy, how we study it as chemists. So we always study the change, final minus initial, but for us as chemists, that's products minus reactants. And then if that difference in products and reactants is a negative value, it would be an exothermic reaction. If it's a positive value, it would be an endothermic reaction. I hope you guys found this helpful.